This is the screen input, and
Maybe you can record at your end also, at least 1%, because I hope I will not be having any audio problem. Audio should be coming. So uh, there is a setting which allows the audio to be recorded from the application. I hope that is applied. Let me check audio setting. You can record it from your side also when you're, you know, just for the sake
okay.
of safety. Yes, go ahead.
So
So
I don't think in my side there is any recording option. I don't like from any schools.
you don't have recording option.
No, sir.
Anyway, so let's go ahead. I think in the previous sessions also where somebody else is sharing screen and speaking, the audio comes, right? So you have checked that I'm recording and somebody else is speaking, audio is coming.
Yes, sir. I checked in
Okay, then
the
go ahead.
settings. So this is the output which I'm getting. So this red one is the computer output. Overall, it's like this. This green one is V in, and blue one is my VREF. So I fixed my VREF at 0.5 volt, and my V in I've ramped steadily from 0 volt to 1 volt over a period of 1 milliseconds. That is, the slope is 1 millivolt per microsecond, as the clock time period is 1 microsecond. So
Yes.
zooming it. So this is where the computer turns low, and at this point, sir, as you can see, my V in is 500.4 millivolt. Sir, this I had a doubt. Then, how will I understand what is the exact resolution from it?
No, if you
So
have
is
to,
it just
so this is definitely showing that it is better than 1 millivolt, right? So within 1 millivolt, it is able to resolve. So that is very sure. Is that clear?
yes, sir. Yes, sir.
So if you have to see how much better, then the only thing you have to do is you have to reduce the slope so that it changes by a lesser amount in a single period.
Okay, sir. So, uh,
Are you getting the point?
yes, sir. So I'll just then I'll run it up to 10 milliseconds. Then I'll reduce the slope. Uh,
It take a huge amount of time.
speaking.
You could have tested it only around that point rather than going from 0 to that point. Min max the voltage range you could have set properly so that we don't have to simulate for the entire range.
Okay, sir.
But anyway, let it complete. So this is
I think I can pause now.
yes.
And now it's going uh, low at around 499.94 millivolts at a lower speed.
Yeah. So that means in the next cycle, so here even for zero point 0.1 millivolt, it is able to do it. So the resolution is better than zero point 0.1 or 0.05 millivolt in this case, right? So that's what it shows. That even 0.05 millivolt difference, it is able to detect.
Okay.
Is
So,
that
sir,
clear?
yes, sir. So I'll just have to decrease the slope, and then figure out if I want to have pinpoint precision, then I have to just decrease the slope, and from there I'll figure out, right? That's the method.
Wait a minute. Yes. Once again, could you please repeat?
Sir, what I wanted to ask is that, so if I want exactly a pinpoint precision, that what is exactly my resolution, so I just need to decrease the slope, right? Every time, and then check that whether it is getting low just after the crossing point or not?
Yes, you have to see that whatever is the smallest difference for which it is able to switch, right? So here, the moment it crossed, below the zero point 0.5 volt margin, it is going to flip here. So what is the smallest difference for which it is flipping? So here, even for 0.05 millivolt, the moment it has gone by even 0.05, it is switching in the right direction. So that shows that it is able to detect the 0.05 millivolt difference correctly at this clock speed. But it is possible that it does not do it for a higher clock speed. If you do it for a higher frequency, because the difference is so small that it will take larger amount of time to settle. So for higher clock frequency, the same switching may not happen. So resolution, again, it depends upon the operating speed also. So for a lower frequency, you are getting this resolution, but it is very much possible that to simulate with higher clock frequency, it is not able to completely switch. But as far as the definition of resolution goes, at this clock frequency, you are getting better than 0.05 millivolt. Point, yeah,
Okay.
because here the voltage is how much? 499.94.
99.9.
So that's 0.05 millivolt. So this is 0.05 millivolt. Now you can check what happens if you have if you don't have preamplifiers. Right now it is with preamplifier, without preamplifier.
So without preamplification, it's
So
in normal.
yeah, so in this case you are getting good resolution, and you can check whether after this all the cycles it is remaining low properly.
So, uh, um, that's- so there are some places like it is not going exactly low.
It is not going low.
Yes, it's not going low in some places. Like here, so as you can see that it should go low here, but it's not.
That means it is still not able to, so that means you need to see the point after which it is completely all cycles it is going low. So at this point it is still erroneous. So we need to see, point after which it is completely, all the cycles it is going low.
So it's here, this point.
So at that point you can see the voltage, because we need to see that deterministically after that point it is always low. So that means it is able to resolve that difference reliably.
So here I am getting at this point I'm getting 501.1498 volt, like around
That means around
501.1.
that means around 1 millivolt. The resolution is around 1 millivolt. If it is
1 minute.
correctly, if it is correctly able to resolve only after 1 millivolt difference, so that after 1 millivolt drop only all the cycles it is coming low, then we can say reliably that your resolution is 1 millivolt.
After that,
Is
all
that
cycles.
is that
Yes,
clear?
understood. Yes, understood.
Now the thing is, if you put the preamplifier, maybe this will go slightly better depending upon the gain of the preamplifier. So if the gain is uh you know 10, in this case, how much gain did you design it for?
So it was designed for actually tensor. I'm getting around 19 dB of
Yeah,
gain.
so with this gain, you can check what is the resolution you are getting. Is it clear to everyone? How did we measure the resolution? Any doubt?
So how to design for a given gain? Can you please like, tell us that?
So this preamplifier circuit, how do you decide the gain of this? What decides the gain of this circuit?
So the
That's the
sizing.
gain.
Yes, hello. So who is asking? So how do you decide the gain? What decides the gain of this circuit? What is the small signal gain?
So the sizing, I guess.
Sizing of what? What is the small signal gain of this circuit? Yes,
So the sizing of the input transistors and the output transistors.
input transistors and output transistor. What is output transistor? There is no out. What do you mean by output transistor? Yes, what is the output transistor?
So here only the input transistors.
What is the gain? If I'll ask you the small signal gain expression for this preamplifier, what is the gain? This is a little surprising because we have discussed this kind of examples in earlier sessions. So the fundamentals are not clear. Then how will you design the circuits? Anybody else? What is the gain of the circuit? How do you find out the gain of small signal gain of the circuit?
So it will be GM1 by GM2, right? Because since I'm using a diode connected one, like the this transistor is a diode connected,
Yes. So,
it will be
so
GM.
you do the thing, whatever you're doing. So is that clear? Like, Ahwan, how do you find the gain of this?
Yes, sir, yes.
So here using preamplifier, it is going low at 500.05 millivolts,
So
and
you need to see the
subsequently,
point after which it is completely low. It is not changing.
yes, sir, I check. After this point, it is not changing. So you can see this. Yes, sir. It's going low after this point uniformly.
So that means that it has improved it to around point, point 1 or
0.5.
0.05 millivolt. So uh, here definitely once you improve the gain, once you add the gain stage, it will do the amplification of the difference. The difference applied to the comparator stage gets amplified. As a result, it will be able to resolve smaller values. So this is shown here by the simulation. So you can see in the earlier case, it was still uncertain. For certain region, it was having uncertainty because the difference voltage was very small. But now, because of this preamplification, immediately, very soon after the voltage is crossing, 0.05 millivolt of difference, it is able to switch. So at least we can say that earlier case it was around 1 millivolt. In this case, it is better than zero point 0.1 millivolt, and the gain that he has applied is also around 10. So that also conceptually shows that yes, means applying the preamplifier is improving the gain. And remember, why do we need to improve the resolution? Depending upon the requirement, right? So if you are applying this comparator for an ADC design, there, if you are going for higher resolution ADC, that means you have to uh, resolve smaller differences. So suppose you are going for 10-bit ADC. 10-bit ADC means you are dividing the entire input signal range into 1024 level, 10 to the power of to the power of 10 levels. So these 1024 levels uh, it will require, suppose it is around 1,000. So if you have 1 volt supply, around 1 millivolt of resolution is required. But then if you go further, if you want to have say 12-bit ADC, then now it is going to be to the power of 12 levels. And now you need to resolve, 0.25 millivolt. So depending upon the application, you may require higher resolution comparators, and accordingly, we need to decide whether we need a preamplifier or not. What should be the gain of that preamplifier? And these things will also decide the speed, because if you're going for higher resolution, speed may also be limited, because here he is simulating for a lower clock frequency. What is the clock frequency here?
So it's 1 megahertz.
1 megahertz. So it is very much possible that if you simulate it for higher frequency, or say 1 gigahertz frequency, it may fail to evaluate. It may take some more time to settle. So you can just check the settling behavior, how fast it is settling for this value. So just at that edge, if you um, if you zoom along the x-axis, you will see what is the settling behavior, how much time it is taking to settle output waveform. You can see this waveform, it is taking around 4.0005 to 4.005001. So this is again very hard to read. 0.005001.
And I've dictated the difference here. It's around 93 picoseconds.
Yeah, so settling time is very good. So in that case, it can work even for 1 gigahertz. So you can go ahead and try to apply 1 gigahertz clock signal and check. The dynamic comparator is fine, but the preamplifier may not the bandwidth of the preamplifier will be doubtful. We have to see how much it is able to amplify, because the preamplifier, if you do the frequency response of the preamplifier, you will see the bandwidth of the preamplifier. So at higher frequency, the gain of the preamplifier may drop. Remember that frequency response, you cannot do it for the second stage. Why you cannot do it for the second stage? Just like you do the frequency response of amplifiers for the first stage, you can do it. Second stage, this comparator, you cannot do it. Why? Yes, anyone? Why can't we do the frequency response to the second stage?
So because we are applying the separate clock in the dynamic comparator also.
So what? So why can't we do the frequency response? That is the question.
So will the clock frequency affect it?
No, that is not the answer. Right answer. Any other any other person? Why we can't do the frequency response or AC response of the second stage of the comparator? The basic thing. These things should be crystal clear. Why we cannot do frequency response of the comparator? This comparator. Preamplifier you can do, but the comparator you cannot do. Why? Again, very basic thing. And this thing should be very clear. Means I don't know why you are not able to answer this. Yes. Anyone? So are you able to
Sir, is
get
it
the switching
because
correctly? The waveform is not very clearly visible to me. Let me increase brightness. I don't know. Yeah, now it is visible. So, so why it has reversed? So you have changed the polarity of the signal.
Maybe I have used the other output, this output.
Yes. So check the you know switching.
Sir, it is working, but it is settling time is high enough.
Yeah, I mean, settling time is
Response.
becoming comparable to the clock cycle. So that
Yes.
will tell you that what is the maximum speed with which you can work. So once the settling time becomes comparable to the clock cycle, you may not be able to reduce the clock cycle further. So for example, in this case, it is, as we have seen, 100, 200 picosecond. That means even for up to maybe 2, 3 gigahertz of clock frequency, it will work. But beyond that, because the settling time becomes comparable to the clock phase, then it will start giving errors. It will not work properly. So, and remember that we had discussed that concept of corner simulation. So the speed will be determined by the worst case corner, say slow corner. And then we can decide that, okay, at what speed the circuit is able to operate. So anybody would like to answer why we cannot do frequency response for the second stage? That means the comparator stage, the dynamic comparator.
is
Fundamentals,
it because
fundamentals.
we will have to vary the slew rate of the input signal and also the clock simultaneously? No?
No, no. Anyone else? Oh, very disappointing. So what happens in the AC response? Like how do we get the frequency response of any amplifier or whatever AC analysis you do? How do you do it? What is the mechanism? We have discussed this earlier also, right? How do we do the frequency? How does the simulator do the frequency response of all these circuits? Whatever amplifier, whatever closed loop, open loop amplifiers you have done. So how does the simulator do the frequency response?
Sir, we
Sir, it
apply an
uses the
AC.
small signal model.
Small signal model. So what all the small signal model contains? Which small signal model is it? Is it DC small signal model or what small signal model?
The AC small signal model.
AC means what? High frequency, right? High frequency small signal model. So
I think.
we include.
Yes.
So if it is the high frequency small signal model, so what is the problem? Like here for the preamplifier, we are able to get the high frequency small signal model. What is the problem with the second stage? It is not
That
operating in small
second
signal mode, right? It is amplifying,
stage
it is
is
completely
operating in
latching
large
and
signal, right?
going to viridian ground. It is a discrete time signal. It is not a continuous time circuit. So there are two kinds of circuit. One is continuous time circuit. The first stage is a continuous time circuit. Second stage is a discrete time circuit. Only when the clock is applied, it is basically latching the difference between the two input. It is further amplifying. So there is a small, there is a small signal operation happening in the initial stage. When you apply the amplified difference to the input of the second stage, it amplifies it further initially. After that, the latching operation is the large signal operation. It is latching because of the positive feedback of this cross-coupled inverter, and the outputs are settling in the opposite direction. One is going to VDD, another is going to ground. So it's not overall, it is not a small signal operation. You can't apply a small signal model to compute the AC response. Only for the initial phase, for the initial phase when the small signal amplification is happening, you can estimate the small signal analysis, what is going to be the settling time, settling behavior. To some extent you can estimate. So only settling time you can estimate, but overall it is a discrete time circuit. So it is working in a small signal mode only just close to the active age. When the clock in this case goes high, just at that point there is a small signal operation which is leading to the further amplification of the signal, and the currents in the M8 and M9 are differentiated. You get one of them branches, you get larger current, another smaller current. But the moment that happens, it further amplifies because of the positive feedback and goes into the latching mode. So up to that point, you can, up to the point where it is behaving like a small signal, you can apply a small signal model and try to calculate the settling time. But for AC analysis, you need the entire operation to be small signal. That is not true here. It is not working in small signal mode. It is transitioning from the initial small signal operation to complete full signal, large signal mode, right? It's latching. So that's why it's not a continuous time circuit. It's a clock driven circuit, and it is working in large signal mode. There are many discrete time circuits where you have clock driven units. There are ways of doing frequency response of those circuits which are clock driven. Uh, that is called periodic steady state analysis. But that is, even that periodic steady state analysis will not be applicable so much here. There are periodic circuits, clock driven analog circuits, which can, uh, for which you can get the frequency response using that periodic steady state that we will discuss later. But in this case, even that is difficult to apply because it is completely switching. It's a non-linear kind of circuit. Once it latches, it goes to VDD or ground, and it is clock driven. So this periodic steady state concept we will discuss a little bit later when we talk about some units like PLL or clock generators, etc. Any question before we proceed further? This part should be clear, I hope, right? So for small signal, for frequency response, you need to write the small signal model. You need to replace all these transistors by their parasitic capacitances and conductances, GM, RO, etc. Get the frequency response. That is true for the first stage. Second stage, it is not operating in small signal model. Therefore, you cannot apply the frequency response analysis here. AC response will not work. Any question before we proceed further? So the way we are estimating the speed for the first stage, you can estimate the speed by just putting a frequency response. You can see that what is the bandwidth of this. But for the second stage, the way we are estimating the speed, we are just looking at the settling time, that how much settling time it is taking. Based on that, we can decide what is the maximum clock frequency for which it will work. For the first amplifier, because that amplifier is still more or less in working in small signal range, you can still calculate the frequency response. Of course, suppose the difference between V in and Vref is high. In case the V in and Vref difference is high, then even the output of the preamplifier will be swinging. Completely one side will go to VDD, another side close to ground, right? So in that case, the preamplifier will also try to enter into nonlinear region. One output will become close to VDD, another output will come. Of course, it will also have large signal output, right? If the difference between V1 and the Vref is high. But here still we can rely on the small signal analysis because it is a continuous time circuit and it goes into nonlinear mode. It goes into large signal mode only when the input difference is pretty big. For the general case, we can rely on small signal analysis for the first stage. Is that clear to all of you?
Yes, sir.
Any question before we proceed further? Okay, so let us go ahead. So we will. Any other part that was discussed? I think this is the part I gave, right? So this is. I'll briefly discuss. So by now, I think LDO part also we had discussed a bit. So LDO, what point was not clear? All of you have, I hope, gone through the discussion, recorded discussion. What part is not clear?
Sir, in the dynamic comparative part, I have one doubt. Sir, while simulating, during the transition region, like when it was transitioning from low to high output, in some of the clock cycles, I was getting an output of nearly VDD by 2, like 0.6, 0.7. Is that like in
No, in the batch
something
based
wrong with the
this
simulation?
dynamic comparator, it cannot. So which comparator you're talking about? Dynamic or static?
No, sir, the dynamic one without the preamplifier.
So dynamic one without the preamplifier, eventually it should go to one of the values, right? So uh, either it will go to VDD or ground. It cannot, because the latching operation is always there. So if your signals are too close, both the signals are exactly equal, or you are keeping them very close, and resolution of the comparator is not that good, then it may, it may take a lot of time to settle, but eventually it will settle to one of the values. So it is possible that you may be simulating with a higher clock frequency. If you simulate with a lower clock frequency, probably it will settle. So what is the clock frequency you were using?
Sir, I was using a like time period of the clock signal was 1 microsecond.
The same as what he just showed. Uh, so we need to see the simulation. So if you want to share the screen, you can share. So it is possible that if you apply exactly same voltage for that point, it may take a very long time to settle. So for what condition are you talking about? Is it so for example, if your slope is too low and for the entire period the signal is remaining very close to the reference, maybe a very small difference, negligible difference, then it may happen. But you can show the schematic if you want to share. You can. Anybody else face similar problem?
Yes, sir, I'm sharing this thing. Sir, is it visible?
Yes.
So, like in these cycles, like during the transition time, in some of the cycles, it's the value is like nearly zero point 0.7. After that, it is settling final.
Okay. So here it's possible that uh, evaluation phase it is not able to go. So you can plot both the signals, the positive and the negative. So I think both will be settling to the same value, and that means the resolution. You can ultimately say that it is not able to resolve. So for very close inputs, they are, uh, you know, uh, becoming very close to each other, and it is a quasi-equilibrium state. So generally, what will happen is in a circuit you will have some noise also because of the devices itself. You will have some noise, and it will ultimately make it switch to another direction. So right now we are not simulating with any noise. So I hope in the recorded lectures, NPTEL lectures, you have been introduced to the device noises, right? So every device contributes to some thermal noise. Likewise, you may have other supply
Yes,
noise sources. So because of those noises, ultimately it will settle to one of the values. It will not hang in between because there is a positive feedback action. So this midpoint that you get, like you will see that both the outputs will be at this point only. So it is a unstable equilibrium. It will not in real world. It will not happen. It will switch to one of the values because in real world you will have some noise, and that noise eventually will amplify and make it settle to opposite values. The two outputs will eventually settle to the opposite values. Right now, it is an ideal case. You don't have any noise present in the circuit. That's why it is hanging to this point. Like the same thing happens in the oscillator. If you have a ring oscillator, if you try to simulate a ring oscillator, in many simulators, if you do not have the noise activated, because if you don't add any noise, if you don't put any initial condition, the oscillator will not oscillate. It will settle to VDD by 2. All the nodes of the ring oscillator will settle to VDD by 2. But that is not an It is not a stable equilibrium, it is an unstable equilibrium. The moment there is some real noise coming into the picture, the oscillator will start oscillating. So the same thing is happening here. So the two nodes, when they are very close, or whether the input signal is very close, the differential current produced is very close, it is not able to completely switch it. But eventually, in presence of noise, device noises or circuit noises, it will switch to one of the direction. So for the time being, you can just assume that the resolution will be decided by the point where it is completely switching. That's all. You can just confirm
Okay.
this. You will see the if you plot the other output, you will see that it is also hung at the same point. Maybe you can just plot.
Yes. Yes, sir. Both of them are at the same point.
Yeah, so there is an unstable equilibrium. It will switch. So another thing that we have not discussed is inclusion of noise. So in commercial simulators like Cadence, etc., we have option of including transient noise. So in that case, what it does is whatever thermal noises, 1 upon f noise, etc., is going to come from the device, it includes that in the transient simulation. That will also affect your resolution. So if the noise of the devices is pretty bad, then your resolution will be affected by that noise. Because the noise itself is several 100 microvolt. Now if the noise itself is 100 microvolt, then you can't resolve anything lower than 100 microvolt. So in many cases, the noise of the devices may also limit your resolution. Right now, we are not including that noise in the your simulation, but in certain cases, noise may be the limiting factor. Okay,
But in
so
LT, I
any
believe there is some noise sources there called PV, behavioral voltage. We can assume we can give white noise
LT
using
Spice noise model I have seen, it does not behave very well. So that is for noise analysis you can do it. For transient noise, I don't think they have a model. So the noise analysis separately you can do, but in transient, I don't think you can. There is an option of
transient
including.
also. They have one called BV, but it does not. It can model white noise, but it's not very accurate.
Yeah, so that is, if you simulate with that white noise, probably it will switch to one of the directions, but it will not be the actual noise contributed by the devices. Okay, anybody else has any other question? So I have not yet, tried that. I'm not getting time to do that X circuit, X schematic thing, because that is very close to Cadence. I have seen that it has also, it allows you to build boxes, hierarchies, different modules you can put inside different boxes, and you can make a whole hierarchy. That is something we are going to need for the next step when we, simulate that entire application for the seizure detection. So maybe I'll have to spend some time to figure out what are the setup issues. So somebody had tried it, right? So I think Satanu had tried it. Satanu.
Yes, sir, I tried it, but it did not work for me because it's sort of it was very
Okay,
difficult to work
so
it out on the presentation.
okay, I will have to spend time and figure out, because that tool, it seems like it has some features which are good and useful, and similar to Cadence. So Cadence, eventually those who decide to work on real projects, we will introduce them to Cadence. We will give them the login, etc. But right now for this course, next few days at least, we will try to complete the application. At least maybe at max couple of weeks, and then maybe those who feel interested, we can, those who are interested in working on projects further, we will introduce Cadence to them. That will take some time. For the time being, I think for the initial learning, LT Spice is okay, but I will try my best to get this issue resolved for this X schematic, so that we can use some better features, especially needed for bigger designs. So I will look into that. So let me share the screen and discuss few things about the next step. This recording I will stop and I will start a fresh second recording. So in the seizure detection scheme, we had discussed there are some online data also available for seizure, which you can use. So it is something like this, right? So or let me draw it a bit more elaborately. So during the normal period, it will be having small noises. So the every signal that you are getting from different electrodes in the brain or outside on the skull, you will have this kind of small noisy signal all the time. But when the seizure comes, it will basically start, larger amplitudes will come. So this is what happens. Now, in case of signal processing, there are several simple techniques also people have tried to apply in order to implement this. So first thing is, of course, if I tell you that how will you detect logically, if I see that this is the behavior, so the target is that we have to detect the onset as soon as possible. So the moment this kind of fluctuation starts, as early as possible within the initial period itself, we have to be able to detect it. That is the target. So what do you think can be done here? We have to there are two a couple of other things also. Under normal operation also, you may get occasional spikes may come like this. But when the seizure happens, there's a large number of, continuously you have large spikes. So this is the signal behavior. So we have to, first of all, before we design anything to implement an operation or implement an application, we need to understand the signal. So the signal is such that under normal condition also some big spikes can come. It is not that the big spikes will not come, but when the seizure happens, continuously big spikes come for a sufficient duration, long duration. It can be few seconds, it can be several tens of seconds. So that it can be couple of minutes. So the target is that as soon as possible, as soon as the onset of the seizure occurs, we are able to detect it. So what circuit can be applied here? What all will be needed based on whatever you have discussed so far? Um you have studied some basic building blocks. So you have studied the open loop amplifier, high gain amplifier, feedback amplifier, how to make feedback amplifiers out of it, how to use buffering. You have studied comparators, static comparator, dynamic comparators, sampling. You have studied sampling. You have studied digital blocks. In the recorded lecture, you have gone through the digital modules like flip flops, counters, registers, and some control logic, etc. So some basic digital circuits also you can do, digital gates, fan outs, sizing, all those things you have studied. So based on all this information, how do we like what do we apply here? How do we design?
That first thing will be requiring an amplifier, right? Because these signals will have a very low amplitude, so we
Yeah,
need
so that is
the
given. You
amplifier,
will need
and
an
also
amplifier. So that is obvious. So very first stage,
we'll
you
need to stabilize it in the noise region, right? Because these circuits may have maybe of low frequency, and in amplifiers we will have 1 by f noise in the low frequency range. So we need to then use proper stabilization, maybe I think, and then
will polarization. I
uh,
have not taught you people. I think it is there in one of my recorded lectures. So have you gone through that lecture?
yes, sir.
So right now I have not covered it. So for the time being, I will not consider chopper stabilization. It was a simple concept only, but for the time being, assume that we are not looking at that. What else? So assume like, yeah,
Then
means
for
noise sizing you can do. So the noise can be taken care to a certain extent by proper sizing. So I guess I have given you some recordings in which the noise analysis of single-ended as well as differential amplifiers were discussed, right? So all of you have seen that lecture where the noise analysis is given, how the sizing of the devices, bias current of the devices, etc., affect the input referred noise. This entire concept of input referred noise. How many of you have gone through that? Okay, so more or less, it seems like hmm, so everybody has raising hands, so I can ask some questions in that case. See, some people withdrew their hands. So 20 people have gone through, and rest 10 people, 8, 9 people are not going through. So I think some people are not taking the recorded lecture seriously. So it's double-edged sword. So if you raise your hands, you can be asked questions. If you don't raise your hands, you have to bear some, remarks. That is less risky, bearing some remarks. So, so the noise chapter, like the lectures on the noise analysis, is important. You should go through that, and the sizing eventually. Right now, in the LT5, the problem is that the noise model we have seen, it is not very correct. It doesn't work properly. That's why I did not emphasize on noise, because noise will be, unless you can simulate it, unless you can make use of it, what is the point? When we go to cadence, there the noise analysis will be accurate, and there we can do the sizing for mitigating noise. But conceptually, in those lectures that are recommended earlier, the noise analysis is given, and it is shown that how the device sizes, input device size, load device size, bias current, all those things, how do they affect the noise of the amplifier? That concept is given, and that is important for any design, especially for the front end amplifier, which is just taking the raw signal. Because for the front end amplifier, because it is processing the smallest signal received from the outside, the noise contribution of the devices is very critical. So we need to be aware of the device sizing issues related to noise. So if you have not gone through that, please go through that. Anyway, so you can drop your hands. So first is the front end amplifier. I can call it the front end amplifier. What else?
Then we'll be needing some comparator, right? Because we can detect the seizure as soon as the voltage surges up to some part. So we will have a threshold for that. So if it crosses the threshold voltage, then there will be chance for seizure. So we will have a comparator also. And
You are saying
then
you will have
also,
a.
sir, we have a,
So what will you compare it with?
sir, you should know some the V threshold, right? Like beyond some threshold voltage, it should exceed the voltage so that we can understand that it is entering the seizure region.
So the question is, how do we, how do we decide what is the VREF? Yes. How do we decide? How do we decide what is the gain, the closed loop gain of the first stage A? Yes. How do we decide? Yes. Any idea? Anyway, so we will talk about that later. Let us see. I will discuss all these things, like how do we decide A, how do we decide VREF. At least the A part, conceptually, you should be able to tell. How do we decide A? Anyway, so we will discuss. So what else? So anything else after comparator? What will you do?
Then we may need a counter because to prevent false alarms, like you said that the voltages may surge suddenly and then again fall down. So that's not a seizure, right? So we may have some sort of counter which will tell for how much time the voltage peak is surging, and then we need some sort of we should compare the time that if the time is greater than some particular threshold time, then it is a seizure. Otherwise, it's not a seizure.
But the comparator output, it will give you what? Like, what are you going to count here?
So like the comparator is high, right? So when the comparator is low and then it again goes high. So as soon as the comparator goes high, I will turn on the counter and then I will tell that like for what time my seizures like this spike signals are persisting.
The comparator output will be something like this, right? So in this seizure region, it will be going up, down, something like this. Depending upon the signal, it will not be exactly periodic. It will be, when the seizure appears, when the signal here is fluctuating at large amplitude, the comparator output will keep going up, down, depending upon the signal fluctuation. So what are you going to count? Are you going to count this number of pulses at the comparator output?
So we can trigger a timer.
So trigger timer, what is the logic of that? So that's what I'm asking.
So means so once the timer is triggered after a certain amount of time, if the output of the comparator is still high, then we will like trigger a flag.
No, so output of the comparator is still high means what? It is not going to be continuously high, right? It's going to go up and down, up and down. Because remember, like,
We need to count the number of pulses of the comparator pulses. Like if the pulses are too high, then
so
it
you
will
will
be a
count.
seizure.
So how will you count for how long? How will you decide?
So we can keep a pre-decided threshold that for n number of that we will count n number of pulses, and once n number of pulses are counted, then
No, n
I
number
will
of
be.
pulses is not the solution. So you can't count n number of pulses. You need to count for a certain duration. If in a certain duration, you have to fix that duration that within a certain duration, say evaluation t eval, within a certain duration t eval, if the number of pulses are greater than some value. So if you're getting, too many pulses versus too less pulses, right? In some cases, you're getting very few pulses here and there versus you're getting too many pulses. So within that T eval, you have to apply a threshold on number of these pulses. That means the count. So this count needs to be compared with a reference count. This is a digital comparator. You understand? Digital comparator, all of you know, digital electronic circuits you have studied.
Yes, sir.
So here you need to compare that counter output with a reference count.
Sir,
So
can we use a VCO? So since we have a voltage regulating, so we can use some voltage control oscillator, right? So if we see that, like if the frequency of the oscillator is quite high, then we can say that there's a seizure. Like that can be done.
so frequency of what is high? So ultimately, so VCO, what are you going to apply to the control voltage of the VCO?
Like if I apply this pulse at the control, then the frequencies will be like quite high, right?
What is the point? So it
So
will go high, low, high, low. So when this signal, what do you want to apply? This is a digital signal, right? The comparator output is a digital signal. Either it will oscillate or it will not oscillate, right? What is the rationale of using that? Are you getting the point? Because if you zoom in, if I just zoom in this portion, it will be something like this and this. We are going to apply this to the control voltage. What will happen? Oscillator will oscillate here. Again, stop. Again, oscillate here. Stop. What are you going to get from this? So that point is not, there's no point of putting a VCU. Are you getting the point? Like, why are we putting a VCU?
yes, sir, yes.
So here, what I said is we are going to have a digital comparator which is going to compare the counter output with a reference count, but it has to compare after a certain period, and then after that period, what do you need to do? You need to reset the counter, right? So because ultimately within a given period from T eval, you started the counter operation. So the counter, if I plot the digital value of the counter, so starting from T equal to 0, so T equal to T eval, the counter will start counting from 0. It will go on increasing, increasing, increasing. This is the output. Like there's a 4-bit digital word, whatever, 8-bit counter, then 8-bit digital word. So the I'm just looking at, suppose this is the 8-bit counter. So 8-bit uh, value, whatever the decimal corresponding to decimal value, I'm plotting along the y-axis. So this is the counter count. So from t equal to 0 to t equal to t eval, whatever count value comes, it will go on increasing from 0 to whatever. And then after t eval, we need to reset it. And then again, it will increase, increase, increase. So we have to see that within this, after the end of this t eval, what is this count coming? Is this count greater than the reference count? If yes, then what does it mean? That within this T eval, we had too many pulses coming from the comparator. And that means that there is a seizure occurring. Is that understandable? Is that
Yes, sir.
clear? But definitely after the T eval is over, we need to go back and reset the comparator. There has counter, so there has to be a reset, which is going to periodically, do the reset operation for the counter. So there are many parameters: the gain of the amplifier, the resolution of the comparator, maybe counter, how many bits in the counters we will be needing, and the T eval that will be required. All these things are design parameters. And now here, if you look at the counter bit, how many counter bits we will need? What will decide that? 4-bit, 5-bit, 8-bit. What is the number of bits? Yes. Anybody? How will you decide the number of bits?
So we can decide according to T eval, right? Because at least it should be able to count something more than T eval. So
What do you mean by
depending
something
on
more
that,
than T eval? T eval is the time duration. So what do you mean when you are making a
yes,
statement? You should
T
be
eval.
accurate, right? So counting something more than T eval means what? T eval is the time duration.
Sir, it will depend on the clock frequency, like how many clock cycles there are within T1. That should be the maximum count.
Clock frequency. No, this is not depending on clock frequency. Ultimately, it depends upon the signal. That signal, what counts as a seizure and what does not count as a seizure. So under the seizure operation, under the seizure, occurrence, uh, what is the number of pulses expected during a T eval duration? What is the number of pulses expected? That comes from the signal. We need to observe the signal, study the signal. We need to study all those, waveforms recorded during seizure, and we need to look at this count. That how do you how many pulses are coming within that T eval duration? Even T eval is a parameter. Like, what is the evaluation period? Is it going to be uh, 1 millisecond? Is it going to be 10 millisecond? Is it going to be 100 millisecond, 1 second? What is the T eval? So that also depends upon the characteristic of the signal, right? So ultimately, how quickly, when the seizure is appearing, how quickly we can detect, and what is the frequency content of the signal. So if the frequency content of the signal is very high, suppose several, 10 to 100 kilohertz signal, so within few milliseconds also you can detect, right? So if this frequency of seizure is, suppose up to 100 kilohertz, then even within few milliseconds you can detect. Within 10 100 millisecond at max, you can easily detect this onset. So time domain detection, it can happen pretty fast. So the target is to be able to detect it as fast as possible, so that it does not lead to full blown seizure and the person goes into convulsion. So for that condition, we need to detect it as early as possible. So now, if the frequency content is told to you that frequency content is up to 100 kilohertz, then we can target that. Okay, within 1 millisecond, how many pulses you are going to get? 100. So within maybe 100 milliseconds, you will get large number of pulses. So based on the data, based on the observance of the data, we can decide that okay, let us target say 100 millisecond of detection period. So T eval equal to 100 millisecond at max, 0.1 second. That means now that 0.1 second, if you are able to detect, then definitely the further effects can be suppressed. This is a very good detection period. If you are able to detect anything, any seizure onset within 0.1 millisecond, sorry, 0.1 second, that is a very fast detection. But then we have to be accurate. We need to make sure that within 0.1 second, it is able to make the right decision. It is able to detect correctly, and it is not going to give us false alarm, right? That is called false positive. It should not give us false alarm. So suppose this is based on the frequency content. I saw that okay, 100 millisecond. So 100 millisecond, what should be the count, maximum count value? Now, if the maximum frequency of occurrence, or I would say the maximum frequency content is around 100 kilohertz. So within 100 milliseconds, how many pulses we are expecting? 100 into 1000, so 100,000, right? So 100,000, we may not require to count that 100,000 pulse. So within this duration, you're going to get 100,000 pulses. So we may not need to count all these. Uh, so we can decide that, okay, again, based on the detection mechanism, because if you try to count all these pulses, then you will require huge number of bits in the counter, and that will slow down the detection process itself. So the counter will be very big and it will be consuming a lot of power if we have so many bits, right? So here we are talking about 100,000. So 1,000 means 10 bit, and another 100, that means another at least 7 bits. So 7 plus your 17 bit counter may not be required. So if you reject it in the beginning itself, maybe we can do it with, say, just 10-bit counter, so that if as soon as it is getting 1,000 such pulses, high frequency pulses, within that duration it can detect. So again, it is a parameter, it is a decision based on the signal, based on observance of the signal. We can decide how many pulses we need to count to reliably say that yes, it is a seizure signal. So that is the signal processing part. So before designing the circuit, we need to look at the signal and apply that algorithm and say that, okay, in all these hundreds of seizure data that is recorded and reported, if I keep a count threshold of 1,000, then is it giving me correct result for those hundreds of patients? The recorded data is there. If I apply this algorithm, conceptual algorithm, mathematically in the code, and if I keep this count of 1,000, is it giving me good accuracy? All those cases it is correctly able to detect how many failures are coming, how many cases it is failing. So that's how, in a signal processing mode, we will decide upon these parameters, t eval and the threshold, the ref count, etc. Ultimately, we will test this algorithm over a large number of models. You can definitely code this, right? So if it is given as a code, forget about circuit design. If a computer science guy is given this as a code, he can code this functionality, that, okay, you are having the signal, you amplify the signal, multiply the signal with a parameter, and then compare with the reference, and then put a counter, and then apply a digital comparison. So this thing can be written in a code form, right? And a signal processing person can do that coding. You can do the coding very easily with a very simple coding for this in MATLAB or Python, whatever. And then you can test this code for real data. Suppose a website has all the seizure data for many, many patients. You get that data, you compare, you basically apply these parameters of this t eval and reference count, and you can check that, okay, for what reference count it is giving me decent result. If I reduce this reference count too much, what will happen? If I go for very low reference count, what will the problem? I should not make it too high, I should not make it too low. If I go for too low, what will happen?
Should make it false alarms.
False alarm, right? Because even one or two spikes come, few spikes come, it will give you false alarm. If you make it too long, too big, what will happen? It may either it will delay the detection, or it may ignore, or it may miss the onset, because you have given the count to be very big. So this reference count has to be set in this case such that the false positive is minimized, the false alarm is minimized, is almost reduced to zero. So hundreds of cases you are applying this algorithm, hundreds of seizure data you are applying this algorithm. You have to make sure that for all those cases, the ref count is sufficiently high so that it is not giving false alarm for random spurious spikes like this. So you can have a series of bunch of random spikes like this coming at any point, right? So for these, it should not give you false alarm. So the count should be sufficiently large, but it should be just large enough. If you make it further higher, even after the false positive has become zero for all those cases, you go on increasing it, there is no benefit. So we'll just stop there. That's how we will determine the reference count. So we can say that what will happen, if this is a false positive, number of false number of false positive, the y-axis false positive. So you are taking, say, hundreds of patients data, seizure data is given to you, and you're applying this algorithm, and on the x-axis you are varying the parameter, the ref count. And for a very small ref count, you will get large number of false positive, and after a certain ref count, it will drop to close to zero, it will become zero or close to zero. So then after that, increasing it further beyond this, it doesn't make any sense. It does not give you any benefit. Therefore, we'll stop close to this point, right? That is how we will. Did you understand this plot, right? This false positive, number of false positive means out of those hundreds of patient's data when you are applying this algorithm. Suppose in those 100 data, there are, 100 seizure points, or out of those 100 seizure signals, how many cases uh, it is giving you false alarms. So I mean, basically, even if there is no seizure, it is giving detection, because you have kept the counts so small that even a little bit of ringing happens, which is not actually seizure. It generates few pulses here, here, and because of these few pulses, it is giving you false alarm. So if you go on increasing the reference count, this false positive will eventually be reduced to zero. Beyond that, there is no benefit of increasing reference count further. So that is the logic. Is that clear to everyone? So I'm just explaining that, okay, given a so you can always do this exercise. I can give you that seizure data, and you can apply this algorithm. You can code either in MATLAB and Python. You can apply, and you can get these parameters like the reference count and the t eval, etc. Right? Even the t eval will matter. So t eval, uh, if the t eval is too big, that also slows down the detection. If the t eval is too small, then again there are chances of false positive. Even t eval, need to be adjusted properly. Is that clear to everyone? So in this case, if I take 1000 as a count, then I may need 10-bit counter. 1000 counter, the 1000-bit, 1000 counter means basically 10-bit counter, 1024. So I can keep a 10-bit counter and compare it with the reference counter. So the other thing is the gain and the reference, right? So the gain and the reference. So how do we decide the gain and the reference? So when you have an amplifier and followed by that, you have already done the pre-amplifier plus comparator. I hope I'm recording right, or I have missed the recording. Is it getting recorded? Let me check. This is, where does it come? So this is here. And I think I have missed the recording. Okay, it's going on, fine. Okay, so going forward, the gain and the reference. So now here you have the amplifier, which is supposed to, you know, uh, give larger signal, amplified signal to the comparator. So the comparator is supposed to basically compare it with the reference. So these two parameters, that what should be the amplifier gain and what should be the reference voltage. Here you are getting some signal, and uh, it may be a small peak to peak amplitude, maximum amplitude may be going to say 10 millivolt, right? And that needs to be amplified and fed to the comparator. So in this case, again, the amplifier gain will depend upon the signal characteristics, that what is the range of signal magnitudes that we are getting. That has to be observed, right? So if somebody tells you that we have the target electrode that will be sitting on the scalp, so this is the scalp, that means your skull, and you're going to put the signal over here. Some people have also designed implantable, which the signal goes inside, the sensor goes inside. So suppose it is outside, and here you are, this probe is basically giving you the data to the chip. So the chip is sitting here, you have the amplifier here, you have other things, ADC and everything after this. So this, ultimately I will have to observe what signal magnitude I'm getting here, right? Based on that, I can decide what should be the range of gain. And in general, what happens is that the gain, or basically the signal amplitude, may vary significantly from electrode to electrode, and based on where you are placing the electrode, and therefore people keep some variability in the gain. That means they keep some tunability in the gain. So this arrow indicates it is a tunable gain, variable gain amplifier, VGA. VGA means the variable gain amplifier. Just like in the rheostat, you have a resistor. When you put an arrow like this, it shows that it's a rheostat. It is a variable resistor. Like that, in the amplifier, when you put this kind of arrow, it means a variable gain amplifier. So generally in practice, people have variable gain feedback amplifiers, and then based on the signal characteristics, so the automatic control of the VGA can be done. Manual control will involve that. Okay, you just test that amplifier, you observe this signal, and you set the gain such that for the maximum peak to peak signal, it is in this case, not saturating completely, it is able to amplify. So that should be the strategy. So again, the A value will depend upon the signal range. So if somebody tells you that this sensor will give you the maximum peak to peak seizures that will come, it will give you something from 1 millivolt all the way to 100 millivolt. That means, or say 10 millivolt to 100 millivolt. So in certain cases, the seizure signal may be just 10 millivolt. In certain other cases, it may be as high as 100 millivolt. Or I can go for more extreme values. In certain cases, suppose the seizure signal is only 1 millivolt. So depending upon that, I will have to tune the range of the gain. If the seizure signal itself is 100 millivolt, uh, in that case, you may not even require a lot of amplification because the signal is already pretty big. If it is 10 millivolt, again, if I look at the signal, the onset side, so gradually it grows, right? The envelope grows gradually. So if I look at the envelope, if you keep the uh, amplification high, what it will do, it will amplify even the initial onset signal and produce large signals because of that. After that, when the signal is completely high, then it will completely produce VDD ground, because when the signal becomes very large, what happens, the amplifier output will saturate, right? So if the input itself is fluctuating by a large amount, the signal to the amplifier itself is pretty big, then the output will fluctuate completely to VDD or ground, VDD or ground. That's what will happen. So initial pulses will be smaller, but finally it will completely go to VDD or ground. So again, uh, if you are trying to detect the onset, you'd like to detect even the initial rising of the signal. So in that case, we will have to have gain so that it is able to amplify even the initial surge. So again, all those things are signal dependent. You based on the signal characteristics you have to observe and set the gain. So in this case, suppose here suppose I have to cater to this entire range of signal, and for that, after the fabrication of the amplifier and after the testing the signal, we see that the actual signal which is coming from the sensor in the case of seizure is just 1 millivolt. Then I will have to do more amplification, and then the variable gain needs to be increased. It will be set to a larger value. If I say that okay, my signal is 10 millivolt, in case of seizure occurring, the signal is 10 millivolt. In that case, the gain will be lower, so I can set the gain to be lower value. Generally, how do we set that gain? So in the variable, ultimately these gain are dependent on the capacitive feedback network. You have seen that amplifier with capacitive feedback. So all we need to do is in the capacitive feedback network, you have C1 C2 ratio. So you have C1 and you have this C2. C1 C2 gain is minus C1 by C2. You may have some reference voltage here, whatever, and the signal is coming here. So if you have this configuration, all I need to do is make the C1 C2 ratio tunable. And out of these, which one is the bigger one? C1 is the bigger one. So it will be easier to basically tune C1. So I can divide C1 into, I can keep it as a parallel bank of capacitors, and I can, have a binary weighting scheme. So this will be C naught, 2 C naught, this will be 4 C naught, and 8 C naught. So I have this total value is, whatever maximum, whatever maximum gain I want, because ultimately it's C1 by C2. So the maximum case, all these capacitors should be connected. Minimum gain case, only the lowest one will be connected. So it's a binary weighted. So how many different, if you have 4-bit tuning, how many different possible combinations of gain are there? 16 possible. So you have 16 possible levels of gain. by doing this. So in this case, how will you do the tuning? So you have to put a switch. You have to put a transmission gate based switch over here, so that conditionally it connects to the input signal. So now if the switch is on, then this capacitor will be coming in series with the signal and will be applying to it will be participating in the amplification. If it is cut off, then this capacitor is not going to play any role. It will have some loading effect. If you want to avoid the loading effect, you can put a switch on this side also, so that you cut off the switch from both sides. Sorry, cut off the cap from both sides. So generally, you can put the TG. This side I have not left much space, but these dots that I'm putting, you can put the switch there. So both sides you will have switches. And in case you want to, include that capacitor, you turn on both the switches. If you want to exclude them, you turn off both the switches. Suppose I want full gain, then I will turn on all these switches. On left side and right side of the cap, I will turn on all the switches, and in that case, the gain will be maximum, right? Because net cap is 8 C naught plus 4 C naught plus 2 C naught plus C naught. That by C2 is the gain. But if I want to have minimum gain, I will turn off all these switches. I will turn off all this, and this. Also on this side, if you have switches, you will turn off all of them. You will keep only C naught. In that case, the gain will be C naught by C2. Right? Is that clear? So this is the way we can generate variable gain. And remember, in order to turn on these switches are ultimately TG, right? So transmission gate. All of you remember the transmission gate? I think in some lectures it has been covered.
Yes.
Ultimately, these will be TGs, and you have to, if you are turning it on, you have to apply VDD here, ground here, and what else do you need? So you need some register the state. So you need a flip flop which you can program. So depending upon your tuning option, you can either sorry, this is Q and this is D. So if you want this switch to be turned on, maybe you can set the Q to 1, and this Q will be driving this gate. Likewise, for each of these switches, you will need one flip flop, which can store the tuning bit. That is called tuning option. So you will need, in this case, 4 flip flops, which are going to store the tuning bit, which are going to connect to these switches, which are going to decide whether the switches is going to be on or off. Likewise, in design, many cases for many different modules, we require tuning options, and those tuning bits are generally stored in flip flops. So using your initial reset operation when you are loading your data in the circuit or in the chip. So in the chip, you will have this tuning option available. So these are the flip flops. So 1, 2, 3, 4. This is a 4 flip flop register, 4-bit register. Now you will from one of the pin of the chip, you will insert that data 1, 0, 1, 0. In 4 o'clock cycle, you can enter the data in this flip flop. Now let me draw it more clearly. So this register is having 4 flip flops, and this will be giving you those 4 bits 1, 0, 1, 0. So in the initial starting point, when you are trying to set up the chip, you will enter this 1, 0, 1, 0 in this flip flop using one pin, because it's serially connected. You can pass all these 1, 0, 1, 0. Now these flip flops will be storing this 1, 0, 1, 0, and this will be connected to the switches. And that way you can set the tuning. If you change this to say minimum gain, so you will do 0, 0, 0, 1. By maximum gain 1, 1, 1, 1. So depending upon what you write in these 4 flip flops, ultimately this flip flop output, these 4 outputs will be driving these switches, and that way you can control the gain. So that is called tunability. So in many cases we need tuning, gain tuning, current tuning, voltage tuning. So this is the way to do the tuning. You need to have tuning registers which will be storing the state, and that you can program. The way I'm showing it right now, it is manually programmed, right? I'm telling you that it will be manually entered. You can, in the beginning of the operation, when you are setting up the chip for work, you will manually enter these 1010 using external setup. After that, the chip is ready to use. Likewise, there are many other tuning options. All of them need to be entered. Maybe using a single pin itself, you can enter. Is this clear to everyone? Any question on this? Again, their issues will be there definitely, because each of these TGs will have their own resistance. So effectively, even if they are on, you are having some finite resistance inserted in the series. that will affect the frequency response to some extent. So we need to make sure that those resistances are not too small. The sizes of the switches should be sufficiently large so that the on resistance is not significant. It is not messing up with the frequency response. Any question? So this is one way in which the tunability of the gain can be achieved. Any question? So if it is a where is the pen? So if it is a AC coupled system, right now this is the AC coupled, right? So because the signal that is coming to the amplifier, we are using a capacitive feedback amplifier to amplify it. Output DC level of this amplifier will depend upon the VREF, whatever VREF you're applying. And now this amplified signal will be going to the comparator. So this comparator, under normal circumstances, when there is very less signal, seizure is absent. So the output of this amplifier will be close to VREF, right? So because under normal conditions, when the signal is very small, seizure is very small, or basically there is no seizure. So we remember we used an RF feedback resistor to bias this, and that makes sure that the DC level here and the output is same. And as a result of that, the output DC level will be same as VREF. So in the normal condition, the comparator will be getting the input signal will be very close to VREF. Fluctuation will be there, but it will be around VREF. But when even when the seizure appears, the fluctuations will start. So now, in this case, how do we decide the reference threshold? So this is the reference. So this is the signal coming to the comparator. Everybody understands this, right? So the DC level of this signal will be close to VREF because this is a feedback amplifier we have applied for amplification. And this will make sure that the DC level at the output of this amplifier is same as the VREF because of the negative feedback. So here, now I have to decide this is a comparator. And I have to decide about the reference over here. What should be the reference? So with respect to VREF, whether it should be VREF plus 10 millivolt, VREF plus 100 millivolt, where it should be. It should be here, it should be here, it should be here. Where should I place that reference? So again, if you keep the reference too small, what will happen? This delta that I'm talking about, ultimately it will be VREF plus delta. The reference is going to be VREF. I should call it VREF A, VREF of the amplifier. This is VREF A. So this VREF A is the reference of the amplifier, and the DC level of the output of this amplifier will be VREF A. So this reference will be VREF A plus delta. This delta will decide, the threshold, right? So this delta, whether this should be the delta, this should be the delta, or this should be the delta. So if the delta is too small, what will happen?
Sir, we may get false positives, right?
False
Like for
positive
small
once again. So again, the delta, small delta means false positive because even small fluctuation in the signal, something small fluctuation happens, which is not actually the seizure. Seizure is this, but even small fluctuations, if the this is getting amplified and the threshold is very low, delta is very low, it will count all of them as seizure because it will detect all of them as high pulses. If the comparator is threshold is too high, delta is too low. So again, carefully by the signal processing, by analyzing the data, the signal processing person will tell you what should be the delta, right? So if you are the designer and you are doing the signal processing yourself to understand the specification, you will have to analyze that signal for many, many patients. You have to look at the data, and based on that, you can decide what should be the reliable delta, which does not give me false positive. So again, the plot of false positive. So this y-axis again, I'm putting false positive, and I'm putting the delta along the x-axis. So again, the delta is very small, false positive will be large, and eventually it will fall down to zero, and then something like this. And what will happen to false negative? If I also plot false negative means failing to detect. Seizure happened, but you fail to detect. False negative versus delta. So that is also important. So again, if you keep the delta too high, what will happen? initially false negative will be 0, but delta too high means again it will start increasing. So I have to avoid this also, right? So again, delta has to be chosen such that neither it is giving you false positive nor it is giving you too many false negative. So that will be the region of delta. So delta has to be appropriately chosen by analyzing data. Is that clear to everyone? So again, means
Yes.
while doing the circuit design or deciding upon the specs of the circuit, we need to understand, especially for the analog part, we need to understand the signal. If you are looking at front end signals acquisition system, you need to understand the signal and the kind of processing we want to do, kind of information we want to extract from the signal. Then only we can correctly decide upon the design parameters of the system. So this is clear to everyone. This signal processing example is a simple example, and just time domain processing we are discussing. In other cases, it may be more complicated signal processing involved, frequency transformation involved, FFT involved, Fourier transforms involved. That will be requiring more complicated signal processing. Any question before we proceed further? So maybe it may be a good exercise to actually check some seizure data, apply this algorithm, and see these parameters. Any question before we proceed further? So I think
Yes.
more or less we have seen some of the basic parameters. We have seen the amplifier, the reference, the counter, threshold, ref count, number of bits of the counter. So these are some of the system level parameters. Yes, somebody was saying something. So in this case, intuitively we can see that if the signals minimum signal is say even 1 millivolt, uh, we may not need more than say uh, a gain of say few 10 or 100 at max, because ultimately the comparator it is going to compare that amplified signal with the reference. So even if you are having a gain of uh, say 100, suppose you are having a gain of say 10, and the worst case seizure you have is say 1 millivolt. So in certain cases, the sensor is giving you worst case seizure signal of just 1 millivolt. So now that 1 millivolt, you want to detect that small 1 millivolt fluctuation. That is the target. So that 1 millivolt gets amplified by 10 times and you get 10 millivolt over here. So at the amplifier output, you will get 10 millivolt. Now this 10 millivolt needs to be compared with the VREF. And if the comparator resolution is good, if it is able to resolve very small differences, even 1 millivolt of differences, then as soon as the signal is reaching this 10 millivolt peak to peak amplitude at the comparator output, at the amplifier output, the comparator can do the job, right? If the comparator is nominal and just 1 millivolt resolution also, the moment it crosses the threshold, suppose the threshold you kept is 5 millivolt, your signal processing person told you the 5 millivolt threshold is okay, and then if it crosses 5 millivolt by even 1 millivolt, it is able to detect properly. So in that case, the comparator design is also not very critical. I would say we not require very high resolution comparator to detect a 0.1 millivolt of difference. Not required. Even 1 millivolt in this case is going to be okay, because all we need to detect is whether the signal is crossing this 10 millivolt level. 10 millivolt peak to peak is happening or not. For that, even 1 millivolt resolution is good enough. So I don't need to put a preamplifier. I don't need a very high resolution comparator in this case, right? So we need to understand the requirement. Then based on that, we decide the circuit topology, whether the preamplifier is needed or directly, comparator is good enough. If the signal processing person tells you that the sensor is giving us bigger signal, so 10 millivolts, 100 millivolt signal already, or 10 millivolt signal already, then that 10 millivolt, even if you put a nominal gain, just gain of say 5x, that also will give you 50 millivolt signal here, 50 millivolt signal, and then you have a comparator over here. So definitely it is good to be able to resolve small differences, but 50 millivolt difference and your threshold, given by the signal processing guy is say 15 millivolt. So as long as the signal is below 15 millivolt, there is no seizure, but beyond 15 millivolt, you have to start counting. So in that case, again, the resolution required will not be very high. Within 1 millivolt resolution of the comparator is good enough, right? So those things we need to, but yes, now if your comparator offset comes into picture, what will be the result of that offset? Offset means, effectively you can shift the reference by that offset. Offset means now there is a mismatch, effective mismatch between the two inputs. The reference effectively gets shifted by that offset value. So if there is offset, what will happen? You can do the offset cancellation. In one of the lectures, I have described the offset cancellation. So that offset cancellation can take care of the offset. But if we uh, do not do offset cancellation, because offset cancellation also is a power hungry process, you need to have a continuous offset cancellation scheme. If you do not do that, then what is going to be the result? What will be the effect on that offset? The comparator offset.
Sir, if we don't have the offset cancellation, then the VREF which we apply, the comparator will see a higher VREF, right? So one problem which might that do is that may increase my chance of false positive, false negative, right?
Yes. Yes. So, if the comparator threshold is such, the offset is such that, it is applying a positive offset to the input. That means even if the signal is low, effectively the input will be considered as large and it will be crossing the threshold more frequently. So the comparators can have offset of several, tens of millivolt also, 10, 20 millivolt, 30 millivolt. Especially the dynamic comparator has a good amount of offset. So if that kind of offset is coming, it may be safer to have a larger gain. It may be safer to have larger gain because what will happen if you put a larger gain for the amplifier? If you put larger gain for the amplifier, it will make sure that the signal is pretty big as compared to the offset, right? So if the gain is such that your signal at the amplifier output itself is, coming 100 millivolt peak to peak, then 10 millivolt offset is okay because, still you have to compare. Suppose, the threshold is say 30 millivolt. So 30 millivolt plus minus 10 millivolt variation in the reference maybe still not that, drastic for your. It will definitely affect to some extent, not that drastic. So having a larger gain will help you in suppressing the effect of offset of the comparator. Is that clear?
Yes, sir.
Again, these are design decisions. When you operate with the actual signals, you will understand better. So this is a simple scheme where we are just doing time domain processing and we are trying to detect the seizure onset with the help of some analog processing and some simple digital processing. This is easy to design. You can always, and of course, in this case, the analog block will require a regulated power supply, very less noise. So that will require an LDO to operate. And the counter and the digital output will require a clock. So clock generally for this application, the clock frequency may not be very high. It will be just, as we mentioned, one example, uh, at max, we are going for say count of 1,000 and the duration of the count is say 100 millisecond. So we may not require a very high frequency clock. At max, a few tens of kilohertz to 100 kilohertz clock will be good enough. So uh, in that case, even a crystal oscillators are used to generate on-chip clocks, or sorry, on-board clock, and that clock can be used by this chip. So PLLs are used when we want to synthesize higher frequency clock. In this system, we don't need high frequency clock, so there is no need of PLL as such. Also, PLL are used when you need a very well controlled or controllable frequency, etc. Here, there is no such stringent requirement, so we don't need a high frequency clock in this application. So yes, an LDO will be required for the first two stages. Second two stages can work with a nominal frequency clock obtained from a crystal oscillator. So this part, you already have the amplifier, you already have the comparator, you have seen the lecture on the counter, and digital comparator, you can, based on logic, you can always build the 8-bit digital comparator. So this thing is easy to design for all of you, I guess, not very difficult. And the uh, kind of specs I have given to you, if I assume, say, 10 millivolt input signal, that is during the seizure, the signal is 10 millivolt. The gain required here is low, just 5 to 10 gain. So suppose just closed loop gain of 10, that will not require a very precise amplifier. Also, another thing is that are we considered about the linearity in this case? Are we very concerned about the linearity and distortion? For the amplifier,
Yes.
remember the open loop gain comes from what factor? Open loop gain comes from the accuracy factor, that how accurate the gain should be, right? Because closed loop gain accuracy depends upon the open loop gain, right? So for the amplifier, we have beta, 1 upon beta upon this A naught is the open loop gain. So this approximately is 1 upon beta, provided A naught beta is much bigger than 1. And this we do so that the inaccuracies related to A naught, inaccuracies coming because of A naught, GM, RO variations, and also the nonlinearity which the amplifier is having, because A naught is signal dependent also. Because for the open loop gain, the input signal becomes larger slightly, it will have distortion because it is leaving the small signal operation. Now it is entering to larger signal operation. So we want to have more precision and better linearity. We need to have larger A naught. But in this case, we are we concerned with exactly these precise values? Are we concerned with these precise values? Not really. We are just concerned with the level. We are not concerned with it exactly, whether it is 10.5 millivolt or it is 11.6 millivolt. We are not concerned with that. We are just concerned with the level, crossing level. So exact values, very precise values are not required, and we are, not looking at maintaining the linearity also. Even if there is a distortion in linearity, we are okay as long as it is amplifying the signal. So some of these constraints related to the linearity and the precision will also be relaxed in this case, because we are not concerned with exact signal level. We are not, it is not that we want exactly linear gain. If the signal is looking like this, the amplified one should be exactly linear and coming exactly like this. Even if it is slightly distorted, it is okay. So it is not a linear. We don't necessarily need exactly linear gain. Linear gain means for all signal levels, the gain should be same. That is linear. But here, even if the gain changes slightly, some higher signal level, the gain is little lesser, it is okay. It is not going to kill the operation. So here the linearity constraint is less. Therefore, the A naught may not be very big. We can definitely have lower A naught. So if you have lower A naught, you can trade off, lower A naught means you may have, uh, you can design it with lesser area, smaller devices, lesser current, right? So that will be good for your power consumption, because implantable devices or wearable devices, we need to have lower power consumption, right? So we need to consider that power budget also. What is the minimum power with which I can operate it? Yes, noise may be a concern. If the input signal was too low, say if the input signal was lower than zero point 0.1 millivolt, 1 millivolt, then the input referred noise of the circuit will come into picture. But if the signal is sufficiently big, if the seizure signals are at least starting from 1 millivolt to 10 millivolt, then noise may be less significant. But yes, irrespective of that, we need to make sure that the input referred noise is not too bad, so that it starts corrupting the signal itself. So noise will be an important consideration. Bandwidth, the open loop gain need not be very high. Closed loop gain, as we saw, we are not targeting very high closed loop gain. Maybe just a factor of 10 may be good enough, 10, 20 at max. And within that 10, 20 closed loop gain, we don't need very high precision. Therefore, the A naught can still be low, right? Remember that for 1% accuracy, that means less than 1% error. If the closed loop gain is AF is suppose 20, the A naught should be 100 times, right? 100 times 20. So that will be again 2000 gain. You need to use a cascode amplifier and all. Now, if we I don't need that 1% accuracy in this case. I don't need my signal to be amplified with 1% accuracy. So in that case, I can lower this. I don't need 20,000 gain. Even if the 50 gain is there, I will be okay. So in that case, I can simplify the design to some extent. So again, all these parameters will depend upon the application. So in this case, the power consumption is major thing. So we have to minimize the power consumption and still make sure that it is operating properly with the this analog stages are operating properly. So accordingly, we will set these parameters and try to minimize the power consumption while maintaining the operation. Any question? Any question? Give me a second. Yes, any question before we proceed further?
No.
Yes. Okay, so in LT Spice, I'm not very sure whether you can, in Cadence, there is a way to bring in the outside data. Like the serial data is very much available. You can uh, you can download that data and feed it in the Cadence. In the LT Spice, you have to check. You can always generate this data artificially also. Uh, if you just have a superimposition of some sine waves, you can generate some random data, and with that also you can work. So this is an easy design. It's not a very challenging design, and all of you should be easily able to do it. And here, static comparator versus dynamic comparator. If you see, dynamic comparator will be okay to use. Um, so we, in this case, dynamic comparator will not be having any problem. You can use dynamic comparator. Remember, the advantage of dynamic comparator is that it doesn't have static power. The static comparator will always have some bias current flowing. Dynamic comparator has no static power, only the dynamic power or some transient current which flows during the evaluation that contributes to power consumption. So dynamic comparator is good enough. Now, there are, I can tell you the bigger picture. So in real applications, people have proposed even more complicated processing for this. In fact, this is a paper like this scheme that I just presented. This is part of a paper. It means when I was at Purdue, so some people have actually designed this particular thing. They fabricated the chip, measured the chip. So this thing was actually tested and demonstrated that it works. So um, now some people claim that we need more sophisticated signal processing to make sure that the detection is accurate. This is a relatively simpler approach. It works, but people have proposed more complicated approaches also. I will not go into very detail, but just to give you an idea what kind of things people have also done is that after the amplification. Acha, another thing that you can do, another approach that comes to my mind, why can't we do it like this, right? So before that, so you have the amplifier, and after the amplifier, rather than putting the comparator directly, can I put a low pass filter, LPF, and then the LPF, what will it do? It will, your signal was like this. It will produce a envelope, right? And then you put a comparator, compare it with VREF. The VREF can be here, VREF can be some value over here. So the moment it is detecting, ultimately it is trying to detect the amplitude, the overall envelope of this system signal. Now, after this comparator, what do you need now? You just need to see that the comparator output, it is staying high for how much duration. You don't need a counter in this case uh, to basically, or you don't need to count the pulses. You just need to basically put a counter, and it will be driven by the clock, and this will be detecting for how long this comparator output is remaining high. It is not going to count the pulses. The only change is in the previous case, you were counting the number of pulses given by you are counting the number of pulses given by the comparator output in a fixed duration. So in this case, the counter that we had done, it was taking the comparator output as its input. It is counting how many comparator output pulses are coming within a fixed duration. That is the logic there. In this case, what will be the logic? Logic is slightly different, maybe. Here you are trying to see that for how long the comparator is remaining high. That's all. Because in this case, comparator will go high and remain high till that envelope is there, till that envelope is coming. Because this is a signal envelope. So this is your envelope of the signal that we are trying to detect. The moment the signal starts increasing, the low pass filter output will also show that envelope, and that we are comparing with the VREF. So here all we have to see is that for how long that signal is crossing that threshold, the envelope is crossing that threshold. So in this case, you take that comparator output, and the counter in this case is driven by a clock, not the comparator output, and we are seeing that within what is the maximum count given by it for which it is completely remaining high. Because till it is remaining high, this will be like enable, right? So enable signal is given by the comparator. So the moment it's enabled, the counter starts counting and it counts to a certain maximum value. So till the count is continuously increasing, we say that okay, means this is uh, a seizure region or the seizure period. After that, the count will cease to increase. Once the seizure drops, it will cease to increase. So if we see that, if we want to apply a time domain threshold, we'll see that what is the minimum duration for which the counter is going on increasing, because that will basically tell us that how long the comparator output is remaining high. Can we do this even without counter, without going to the digital domain? Can we do it in an analog domain itself? How can we do it completely in analog domain without even going to the counter? Because counter requires clock, and again, it will have some more power consumption. So if you want to avoid that also, in this case, what will you do? First thing is the low pass filter pole, right? So the first low pass filter pole here will be pretty low, right? Because we are talking about the detection of a few kilohertz signal, and that also we are trying to get the envelope. So this envelope detection, if we try to do using low pass filter, the pole of that filter must be very low, few hertz, maybe few at max few tens of hertz. So again, that RC value will be very big, right? So remember that on chip we cannot have very large resistors and capacitors. So if you are using op-amp based filter, getting that feedback RC very large value, we have to use some special schemes, just like we have discussed last time, the subthreshold resistor to get the very large R, and a capacitor you can put, the on-chip capacitor will be very limited. It may not go beyond, say, few picofarads. It will be of few picofarad range, picofarad. And this R, you can use the subthreshold transistors to get that R. And then based on that, you can make a low pass filter, single, single order or second order low pass filter. But again, the R will not be very accurate, because this R obtained through subthreshold resistant transistors, they are going to vary over process. So you have to make sure that we are able to tune it. We make sure that it is not varying very widely. Those concerns will be there. So it is definitely introducing more challenges, because the LPF design will become more challenging, especially if you want to do it for very low frequency. But suppose we are able to do this, after that, uh, how can we get rid of the counter? Like if we want to do it completely in analog domain and get the decision, what simple circuit can replace a counter? Yes.
The analog timer circuit using a monostable multivibrator or something.
Monostable multivibrator. Okay. So how do we like again? How do we build that kind of like what? How to include that functionality? I'm drawing the comparator output. This is the comparator output. This is the vref of that. You are getting the envelope over here, and you have to see that you know how long it is remaining higher than that threshold. How long the envelope is remaining higher than that threshold. If it remains higher than that threshold for a certain duration, minimum duration, you basically detect it as a seizure. So what is the simple approach? Yes.
Sir, once we will provide this signal as the trigger to the monosyllable multivibrator, and it will be programmed to some pre-decided time duration. And
No, I
after
don't.
it is
Again, that I'm not going for digital blocks. I want to do it completely analog. So no counter, nothing. So here, how will we? So that monostable thing, how will you decide? How will you design? Just suppose you have a clock. Clock is possible. So what will be the circuit implementation? One thing that comes to my mind is maybe you can put a cap and you initially precharge it. There will be a precharge. So when you precharge initially, it will be charged to VDD. After that, you let it discharge using a current source over here. This will be a small current, maybe 1 micro or whatever. And you have to, of course, choose that current properly, and you have to choose that cap also properly. Now, the moment this comparator output goes high, it starts discharging this cap, and then the moment you know in a given time, so ultimately this cap value from VDD it will start discharging towards ground, and if it remains too low, means if it if the envelope remains high for a long duration, eventually it will go to ground. So here we can compare it with another, say, crude comparator C2. You compare it, say, VDD by 2. So the current and the capacitor has to be decided such that during the threshold duration. So we are trying to see whether T within the duration T naught, it should be able to declare it as a seizure. So if the envelope remains higher beyond T naught, it should detect it as a seizure. So what is that condition? So in this case, C dV by dt, that means I dt times this is your charge, right? So I dt. So I times T naught, I ref times T naught is the net charge. So I naught divided by C is the net voltage developed. And initially this should be basically equal to VDD. So this should be VDD. So I dt charged by C, the voltage change, this should be VDD by 2. So the net voltage change in this duration should be VDD by 2. That is the relation between the T naught and C and the I ref. So if you are able to do that, then without any comparator, we can do the job, right? We can say that, if the uh, comparator output is remaining higher beyond T naught, it will make the capacitor discharge beyond VDD by 2, and then it will declare it as a seizure. After that, you go ahead and pre-charge or, again, do the preset of operation of the capacitor. So here we don't need any counter. Is this clear? This scheme is also clear to all of you? There may be other approaches, but this is one possible approach which just came to my mind. So without comparator, without counter, without digital units, this is also one possibility. But the issue is that ultimately you will need to apply, if you're using dynamic comparator, you will need to apply uh, clock to these comparators also. If you're using static comparator, then you don't need clock for those comparator as well. And especially because here the comparators are going to operate at a very low frequency, the power consumption of these comparators can be relatively low because they're not operating at very high speed. Just at max, say, bandwidth will be few tens of kilohertz or at max 100 kilohertz. So open loop bandwidth for this comparator required will be just 100 kilohertz around. Therefore, power consumption may not be very critical. So even static comparator may be okay for this. Is this clear to all of you? This approach is slightly more involved in case of because you are having this RC filter involved, op amp based filter. and then you need another comparator analog domain. If you have to completely do it in analog domain, digital domain, you are having the amplifier, after that directly the comparator, then counter, plus some additional the control loop. So the scheme is slightly different in terms of complexity. Analog side you have added some more complexity, digital side you have simplified some more things. So you have to compare that, okay, which one is better, then you have to compare power consumption, which one is doing better, because the digital circuits, what is the power consumption? CV square F. So the CV square F will always keep running. So the counter is running with some clock frequency, this power consumption will always keep happening. In this case, there is no such counter always running, right? So you are just static circuits are there. So if you make this amplifiers very low power, working with very small bias current, we don't at least have this continuous CV square F frequency coming, CV square F component coming because of the counter. So again, we need to decide, we need to see whether mitigating this CV square F power coming from the counter and the other digital blocks, that is helping us in saving some power. And this kind of things can be true for low frequency signals. Like in this application, it's a low frequency signal. So another variation, like I can give you one higher level thing that people have done. So they don't stop at time domain processing, they go for frequency domain processing. So there will be an amplifier A. After that, they will go for A to D, that means ADC. This ADC will give you high precision recording of that signal, digital value. After that, they will do frequency transform, something like FFT, or they will go for some other frequency domain transformations. And then they try to look at the frequency characteristics, like frequency spectrum of the signal. Suppose this is the frequency spectrum, this is the F axis, and this is your amplitude mod. So this is what they will try to calculate. And then when the seizure appears, it has certain frequency components. So they will try to see that which bands your frequency is peaking. So normal condition, suppose is a normal signal, but when the seizure is coming, it is showing some peak at certain frequency bands. So we will try to detect that in which frequencies, at what frequency the peak is coming, how the frequency characteristics is changing. That is another way, and people claim that it is more, I would say, accurate, because it is not relying only on time domain signal, but it is relying on the frequency content of the signal. So it will be less
Well,
sensitive to noise,
will
etc.
not be so will this not be a little time consuming? Because then like we
Yes, it
need
will be
to
more power
see.
consuming. So FFT frequency domain, the ADC you are introducing FFT. So definitely, as compared to the circuit that we just discussed, this is going to be a lot more power hungry, a lot more complex, a lot more bigger. But the benefit, people have claimed that okay, this can be more accurate. Again, it is subjective. People have reported certain results on seizure data, and algorithmically, if you can show that yes, this is giving us better accuracy, even by 2%, 3% better accuracy, people may be convinced that okay, let us use this. If it is able to suppress the false negative completely, or improving the false negatives by few percentage, then you have a justification. So if you have to use more complicated signal processing, then we have to justify that is it giving any advantage. If it is not giving an advantage, if your simpler scheme is able to do the same job with the same accuracy, false negatives percentage is same, false negative percentage is same, then there is no point going to this more complex approach, because here after the amplifier you are putting that ADC, which is going to be more power hungry, and the FFT is a digital block Fourier transform, which is again pretty bulky digital processing unit, that will also require good amount of power consumption as well as area. There are several others. The FFT is one of them. There are several others. I have also worked on certain other signal processing schemes like DWT, discrete wave transform, etc., where we showed that yes, it gives good detection accuracy. But again, a thorough comparison, the simpler approach with the real data, that can reveal whether these schemes will give you any tangible benefit as compared to the simpler approach. So again, depending upon, as I told you, a signal processing person, if he tells you, I means that yes, uh, this approach of digitizing the data and then doing frequency transform and then looking at the frequency spectrum, that at which frequencies the peak is coming, which frequencies content is changing. So based on that, if I can apply detection, that may be, first of all, it will be less, I would say, it will be less sensitive to the change in the signal, right, signal amplitude, because sensors, depending on the sensor, signal amplitude may change. Some sensor will give you higher signal, some sensor will give you lower signal. Then you have to adjust the gain of the amplifier, etc. So this will be less sensitive to all those things, and also it's less sensitive to noise, random noise, because frequency content is also an important signature of the signal, right? Analyzing the frequency content, you can get important signature of the signal. Uh, because seizure will have its own frequency content, it will lead to rise in the certain frequency regions. So that becomes a little bit more robust, and therefore it has some advantage. So if you have a justification at the signal processing level that yes, this scheme is giving me some advantage as compared to the simpler approach, then you have a case. Then you can justify that yes, this chip, although it is more power hungry, but it is more accurate also. Is that clear? So ADC design also you have seen in a couple of ADC designs, at least a single slope ADC, how to do it, that you have seen. But right now we are not going to go for this. Maybe initially you can just try this simpler approach, the very first one that we discussed, which is, for the time being good enough. Any questions? Okay, so I think this is a simple design. You can go through this, and I will try to look at that X schematic thing. This is a simple one, and you can do it in LT-Spice also, because the number of transistors are not very big. Because amplifier you already have, comparator you already have, counter will have, if you have 8-bit counter, then you need to construct those flip-flops and put them. There are ideal flip-flops available. In LT-Spice, you have ideal flip-flops also. You can instantiate that also, because counter design will not be very sensitive here, because we are not designing very high-speed counter. So even if you use the ideal counters available, even the counter is available, I think, in LT-Spice. So these two modules, the counter and the digital comparator, I think if you take it directly from LT-Spice, it's okay. You don't need to go to transistor level. But in the real chip, you need to understand, you need to be aware how will you design the counter. Because, for example, ripple counter. So we already seen that lecture, how to design a ripple counter. Likewise, digital comparator. So you have seen digital logic design. I have explained the sizing of NAND gate, NOR gate, fan out, loading effect, all those things. So if given the task of designing the counter and digital comparator, you can do that as well. But right now, because it's a relatively low speed operation, we don't, this design of this counter and the comparator is not very critical. In case we go for very high speed operation, some other signal applications where the signal speed is very high, then the digital design becomes more challenging. Lower speed will be less challenging. So initially, you can use the counter module and digital comparator module. I think ready-made modules are available. A digital comparator may also be available in the LT-Spice library. So there are many other things. LDO part I will discuss how to look at the LDO, but signal at this point, amplifier followed by the comparator. I will not ask you to go for variable gain amplifier unnecessarily. That will be requiring too many switches and all that. Right now, don't go with that. Um, So design just you just have to cascade the amplifier that you already have, put a closed loop gain, a small closed loop gain, maybe just around closed loop gain of 20. That's good enough. You may not need a cascode output stage, because here we don't need very high gain. So you may get rid of the cascode output stage. A simple output stage will be good enough. And then after that, you need a comparator. And in the comparator, you don't need a preamplifier also. So taken together, it is just op-amp stage with a capacitive feedback, followed by the comparator, followed by the counter and the digital comparator. So I think this is a small exercise. I don't think it will take much time. It's a simpler modules involved here. And yes, means LDO side, we can try to. We have not done the PSR response. So PSR response, like whether the circuit can handle noise, right? So for example, if I have to see that how much noise your amplifier can handle, because amplifier is the most critical block. So whatever VDD you are putting here, right? So you are supplying it with some voltage source, some VDD, 1 volt. All the circuits inside that you are supplying with the VDD. So in series with that, you can put some AC peak to peak noise, say 10 millivolt noise, and then try to see what is the output signal coming because of this, provided the inputs are at DC, you can see what is the output coming. So that way we can look at, how much effect the VDD noise is having on the output. And then based on that, we can say that how clean supply is needed, whether 10 millivolt VDD noise is acceptable. That will also depend upon your input signal. If the input signal is small, 1 millivolt, And here after amplification, it is gain of 20 to 20 millivolt peak to peak, and you have 10 millivolt supply noise. So you can check how much effect is coming from the supply noise to the output, right? So because we need to make sure that there is not significant transfer of the supply noise to the output. So this analysis will tell you that okay, for a 10 millivolt peak to peak supply noise, is it able to handle how much corruption is happening at the output? So just checking the effect of supply noise, you can keep the inputs at say certain DC. This is a feedback amplifier with the feedback loop AF, and input. Suppose you are applying constant DC, um, and then you are checking the output noise level. And in case this is the signal specification that the after the amplification the signal is 20 millivolt, then we need to make sure that the noise is much less than that, maybe less than zero point 0.1, zero point 0.2 millivolt, so that how much gain is coming from the supply to the output, that is going to be then going to give the PSR, power supply rejection. So whatever is the suppression, suppose 10 millivolt is giving only 0.1 millivolt here, then you have a 100 factor of suppression from the supply noise to the output. But if it is 1 millivolt, then you have a poorer PSR, because 1 millivolt, 10 millivolt out of that 1 millivolt is transferred to the output. That part you can check, and that will help us decide whether LDO is needed, because LDO will be needed, a more precise LDO will be needed if the signal is very small, very weak. Like suppose we have to handle with the sub millivolt of signals, zero point 0.1 millivolt of signals. In that case, it will become even more sensitive to the supplied noise. So again, the regulation of the LDO provided depends upon the signal. So that we can add little later. First, you can at least complete these two things, add the comparator, add the uh, this comparator plus the counter, and complete the operation. Test it with the signal. So signal, in order to create that signal, as I told you, you can just create that signal artificially also. Like let me think. So you can, because that gradual surge will not be so easily available. For that, you have to um use something like let me think. So you can always have one source, which is the DC, and then on the side you can always have initially the switch is there, which is directly passing the DC, and in second case you turn on another signal, which is the AC signal. This is the AC signal, and when you want to apply the signal, you apply this one. So this is your no seizure, no seizure. This is your seizure. So when the seizure is high, or I can write it S and S bar. So this is your SZ bar, then no seizure. And when the seizure happens, this is the SZ. So by controlling that, you can add this noise conditionally, and then this signal will look like something like this, and then on sudden like this. And based on that, you can create. Only thing is that tapering effect will not come like when it is constant and gradually trying to increase. So that also can be done. Means you have to apply some trick to get this kind of tapering effect also. Uh, for that, maybe some variable time dependent gain or something has to be done. That we need to think about it. Um, mm, so one way to do that, maybe uh, you have a common source amplifier, and then you apply the AC signal along with the DC. So the DC can be applied using a large resistor, and this DC will be ramping. So then you can apply a ramping DC over here. That means the DC will gradually go up. So initially when your DC is very low, then the gain may be very poor. No, that will not happen because GMRD. So we need to see some variable gain we need to put so that we can construct this diverging amplitude. For that, this will not work. So let me think about it. So some circuit has to be done so that it can artificially create this diverging amplitude. Um so basically, what we need is a changing gain. Uh, the changing gain easily can be obtained by changing the bias current also for differential amplifier or something like that. So if you have a differential amplifier, if you change the bias current of that, Uh, that can also help. So that will reduce the gain to a certain extent initially. So many things can be done. So if you have a differential amplifier and you have a bias current for this, so as you increase the bias current, the gain drops generally. So now you have the active low differential amplifier, and your signal is coming here, the sinusoid signal, and then you the only problem is how will you combine. So even if you change the current, so current ramp current, is it available? Can you check anybody LT Spice ramping signal is available?
So I think we can generate a PWL file that can ramp. I use the ramping of voltage using PWL in the comparator check resolution setting. There I use ramping using PWL.
So then somehow you have to the PWL file, that option is available. So loading the PWL file as a source, that is available.
Yes, sir. Uh, in LT-Spice, there is an option that we can put at what time we want what value. So it will generate
No,
a
that is
on
the
a
piece by
straight
linear.
line.
So is a piece by linear file option is available or not? Where you have the file
Yes,
upload. Actually, you'll have to check.
yes, file option is also this. File option is also.
File option is also there. Then you may be able to upload actual files, actual serial data.
Yes,
So
sir.
I
So
will
I
just
saw
check.
that. I saw that in the internet. So if we have
Sorry.
the signals and the text, if we have the signal and the text data, that is the if we have the piecewise values of the signal, like the Caesar signal, then we can directly upload it into LT Spice using that PWL file.
That would be better if you already have a piece by linear file option available in LTSpice. Then we don't need to do all this complexity. So then teaser data, I will give you some website link from where the data can be downloaded. I think that data will be in CSV format. CSV format will be something like Notepad. You can look at the data. There will be some numbers in a sequence. So that data has to be fed to the LT Spice source. I mean, the piece by linear file, you need to read that data. So I think directly it can read the CSV data also. You can just check. If that works, then we are done. We are okay. We can directly use the CSV data also. So one of you can check and let me know. If required, I can connect and we can discuss. Otherwise, initial jugaad is this initial, this thing you can do. But for real data, the piece by linear file from the real CSV data can be taken. Is that okay? Any question before we conclude?
So this TREF and VREF that will determine using that taking the data and plotting the false positives and false negatives, right? Like you said,
No, right now
will
that will be
determine.
tough. That will be, that will require signal processing. So if you want, you can do that. For the time being, you can just take some values. For example, uh, based on the signal that you are plotting, whatever signal I give you, based on that, you can decide, because right now getting the accuracy will need simulation with large amount of data. You have to check that for hundreds of patient data, how the accuracy is coming. That will shift the focus towards signal processing. And right now we don't want that at this point. So that for the time being, just take some numbers, nominal numbers. Like I already told you, the closed loop gain of this amplifier at maybe we will need just 20 around. So I'm just already giving you some, numbers. So because if you have to optimize these parameters, that will completely shift the focus. You have to spend time on MATLAB or Python code. You have to do the signal processing, optimize these parameters. That will take time. So that will be another different project. So rather than doing that, for the time being, we just take the gain around closed loop gain 20. Comparator resolution, I already told you, is even 1 millivolt is good enough. You don't need preamplifier. Counter 8-bit, I've already told you. Digital comparator, reference count. Reference count, uh, this for the time being, maybe you can keep it, what, say 100 or something like that, close to 100. Is that okay?
Yes, sir.
VREF, likewise, if you're taking again, if the peak to peak signal over here is maximum, it is going 100 millivolt, keep the threshold of VREF around, say, 50 or 60 millivolt. So if you start doing the optimization, you will have to spend time applying this algorithm to the large number of signals and then check the effect of each of these parameters and then optimize. uh, that is a good exercise that will give you some signal processing experience. If you want to do that, go ahead. I will not stop you. I can give you some signal the seizure data link where the data is freely available. You can download and you can apply this scheme in the code and then get the parameters. Is that okay?
Yes, sir.
Okay, so let us close today, and tomorrow maybe I will discuss some points about LDO, etc. And there are many other modules that we can keep discussing, but while you complete these modules, we can build on some other concepts. There are many other concepts which will be useful to learn before you can get started with some real projects. So in coming days, we'll try to do that. But in the background, you keep working on this. Should not take much time. Means if you're enthusiastic, within a couple of days, even a single day, you can complete it. Actually, it's not a very complicated thing in LT Spice. Okay, but I will give you few days. So because everybody's speed is not the same, so I will give you few days. Take your time. Some people are traveling, some people are here and there. So by the today's Tuesday, by end of this week, you should be able to complete it easily. Friday, something like that. Friday, Saturday at max. Okay. Any question before we conclude? Okay, so let us. No doubt. All right. So stop recording.